Selecting a topic, I thought I would talk about some application of fundamental practice or fundamental knowledge to some practical problems. In the past, when I've done something like this, it's been sometimes in the area of soil mechanics and stabilization of soils, but due to the nature of this conference and all the rainfall that you have here in Costa Rica from time to time, I thought moisture damage might be an appropriate topic. Today I want to give a brief introduction to moisture damage, which most of you will have a firm grasp upon on that topic, and then talk about some ways that we have used fundamental aspects of material science to investigate the materials and the selection of materials that would provide the greatest potential resistance to moisture damage. And then thirdly, to talk about a performance model that we are in the process of developing that is coupled with mechanical analysis, couples moisture analysis, moisture damage effects with the effects of mechanical loading, as well as some other effects. So we'll try to address those three topics. Now, moisture damage itself, of course, occurs because moisture is going to get into the asphalt pavement. And as you know, there are a number of mechanisms that will allow moisture to get into the pavement. First of all, if you have a water table that's anywhere close to the pavement surface, I'm getting a lot of feedback up here, I don't know if you are, but their capillary rise through fine-grained soils will take moisture many meters, depending on how fine the soil is. And once that moisture front moves to within a reasonable distance of the asphalt pavement, thermal gradients and relative pressure, relative humidity gradients can allow the movement of that moisture vapor into the asphalt itself. And of course, the infiltration of moisture through rainfall from the surface is another mechanism. Well, once the moisture gets into the pavement and into the voids, and it diffuses through the mastic, potentially softening the mastic and aggravating the bond at the surface of the aggregate between the mastic and the aggregate, you have the potential for moisture damage. So moisture damage is a complex process, and it is governed by many sub-processes. Thermodynamics play a role in moisture damage. When moisture diffuses through the voids, through cracks, and through the mastic, which is the bitumen plus the fine material, smaller than about 75 microns, when moisture diffuses to that interface, of course it can soften the mastic as it's diffusing through it, compromising its material properties, including strength. And when it gets to that interface between the bitumen or the mastic and the aggregate surface, it can compromise that adhesive bond. And generally we use some concepts of surface free energy to evaluate the potential for that bond to be compromised. So those are thermodynamic principles. Obviously, the interaction between the bitumen, functional groups within the bitumen, chemical functional groups within the bitumen, and the aggregate surface play a big role in the quality and the durability of the bond at that surface. For example, carboxylic acids are functional groups within the asphalt that move quickly to the aggregate surface and bond rather strongly with certain functionalities like silanes at the surface of the aggregate. That bond, however, is not very durable in the presence of water because water tends to rapidly replace that type of a bond. Other functionalities like, for example, sulfoxides and certain other nitrogen groups are more durable at the aggregate surface. So all of these are important properties. And then there's the property of the aggregate itself, the physical properties, the roughness, the surface area of the aggregate, to provide more area for bonding. And we have to account for that. Pore water pressure in the voids is an important factor because that poor water pressure, especially under the dynamic action of moving traffic, can cause a scouring effect that can cause the micro cracks within the mastic and at the interface to grow and cause debonding to occur. And the poor water pressure itself causing a higher static pressure and a higher deviatoric stress can cause more rapid damage within the asphalt matrix. Well, one of the fundamental properties that we have used is surface-free energy. We measure the surface-free energy of the aggregate, and there are three components of that surface-free energy, and we measure it in the bitumen. And based upon those measurements, we can make calculations of the bond strength. And this little picture up here, what we have is a representation of bitumen in the sort of gray, and this represents the stone. So S stands for stone or aggregate. We'll call it stone because of my alpha numerics here, or my designations. And A we'll call asphalt. So this is the asphalt stone interface. In the presence of water, this blue material, that bond can often be compromised. And if you calculate using surface energy measurements, if you calculate the work of adhesion between the asphalt and the stone in the presence of water, we'll skip all the mathematics. When you make those calculations, you get a negative value. And that negative value really means that the stone surface almost always, not always, but almost always, would prefer to be coated with water than with bitumen. Those are just the thermodynamics of the process. So we came up with a little parameter. That doesn't work. We came up with a little parameter to try to evaluate the potential for an asphalt and an aggregate to perform well in the presence of water and therefore to resist moisture damage. So in the denominator, we put the absolute value of this quantity. And so since it's negative, meaning that water would prefer the bond, the absolute value should be as low as possible. The higher that negative value, the greater the potential for water to replace the bitumen. So in our little index, this parameter, the absolute value, we want to be a small number. And then the asphalt itself, in the presence of a dry aggregate, we want it to have a strong potential to wet the surface of the aggregate. And we want that potential to wet the surface of the aggregate to also overcome the potential of the bitumen itself to sort of ball up or aggregate. So that's what this difference means right here. So this means the dry bond strength, essentially, and this is the absolute value of that thermodynamic potential of the water to replace the bitumen. So we want this to be small, and we want that to be large. So that energy ratio would be large if we have a good combination of asphalt and aggregate, or asphalt and stone. And then we normalize that parameter by multiplying it by the surface area, the specific surface area. This little symbol here represents not a true depiction, obviously, but perhaps voids and the tortuous surface of an aggregate. The higher that area and the greater that tortuosity, the greater the specific surface area. So once again, we want that number to be large multiplied by this number, which we want to be large. So this index, which would indicate the potential for good performance between an asphalt and an aggregate, we want to be large. So let's look at some data. We looked at some 14 different bitumens. You can see the PG grade, and the letter just designates a source. We're not interested in the source, where it comes from, but the fact that there are different sources, different chemistries. And then along the top here, we've got different aggregates. You can see that there's some sandstones, some siliceous aggregates, there's some limestones, there's some other aggregates in there. And what I want you to notice is that if we take one specific bitumen, in this case the PG6422B, you can see that this energy ratio that we just defined varies across that spectrum. Now what does that mean? Well, a low energy ratio would mean that that asphalt and bitumen, or aggregate and bitumen, have a strong potential to be damaged in the presence, or a stronger potential to be damaged in the presence of moisture. On the other hand, if that number is large, then the moisture damage potential is low. So what you see is that certain bitumens a certain bitumen performs fairly well with certain aggregates and poorly with others. If you look at a selected limestone or stone or aggregate, you see the same thing. So there's not just a poor aggregate or just a poor bitumen. It's a combination that tends to count. And so I've circled here along these examples in green the low value and in red the high value. So you see that this particular bitumen is very poor with that aggregate. It's real good with this one. This particular aggregate is poor with that bitumen and good with this one. So the combination is what counts. So this little example points to the fact that we can use some fundamental principles like surface free energy of a certain component, bitumen, and the other component, the stone or the aggregate. And by knowing those components of the surface free energy, we can calculate the dry and the wet bond strength and come up with this energy ratio. So you say, well, how does that match with mixture performance? Well, we have got a big database, and I must say that you just can't go out and compare it with everyone's database, because when you get into all the mixture variables like density and air void structure and binder content and so forth, those things overpower these evaluations. So you have to be very careful in comparing performance data from the laboratory with these energy ratios. But just to give you a little example here, this is a direct tensile fatigue test. And we tested it dry, and then we put it in a moisture conditioning environment under a vacuum soak, and we tested it wet. And so the ratio of that modulus test is here. Up here are good values, down here are poor values. And this is the log of our energy ratio. And you can see that when those energy ratios are high, we usually get good performance. We got a fair amount of scatter. And when they're low, we get lower level of performance. The red dot lines represent a 95% confidence interval. So pretty good basis for comparing the energy ratio concept with actual laboratory performance. And once again, I was over in Qatar, over in the Middle East, a few months ago, and a good colleague of ours looked at this, used this energy ratio and compared it up against a large database of mixtures. And there's a fair amount of scatter, and meaning that the correlations are okay, but not great. Well, the reasons that you got to be suspicious about that is because the overpowering influence of mixture variables. You've got to have a very controlled experiment to make that comparison. Now let me shift a little bit and talk about another technique that we have used. It's still based upon fundamentals. This was based upon surface-free energy. This next test is based upon a measurement of the enthalpy, or the heat of reaction between a bitumen and an aggregate. Obviously, warm mix asphalt is a topic of great interest to everyone, because producing asphalt at lower temperatures means that we can produce asphalt with less energy expenditure, asphalt mixes, paving asphalt, and that we can do it with an environmental savings. And you know all about warm mix asphalt. Obviously, we're producing it at lower, considerably lower mix temperatures. A question comes up. what compromise do we make when we produce asphalt at these lower temperatures, and is it of consequence? Well, we used a technique to measure the heat of reaction, the enthalpy, that's given off when you add an asphalt to an aggregate. So what we did is we took asphalt and we mixed it with toluene, which by all of our knowledge and with our colleagues at Western Research Institute has a minimal effect on the compositional aspects and the interaction aspects of the bitumen. So we mix it to lower the viscosity, and we inject with a hypodermic this solution into a vial that contains a certain aggregate, certain mineral or aggregate, and we measure this heat of reaction, which is a direct indicator of the bond strength that can occur, the adhesive bond strength. And here are some examples of the measurements. Here you see two different bitumens. They're different PG grades and different sources, and they're 2 by 2. So these are the two bitumens with a basalt. These are the same two bitumens with a siliceous river gravel, SRG, siliceous material. And then there are the two bitumens with a limestone. Now the limestone is not a pure limestone. It has some siliceous component to it, but it's predominantly a limestone. So here are the total energy of adhesion, the total energy based upon the enthalpy calculations with the process that we just looked at. And you can see that each combination was treated in a different way. The blue represents the fact that the aggregate was heated to 90 degrees C before the experiment. The green, or the gray, represents 110 degrees C processing of the aggregate before the aggregate was injected with the solution. And then the red is 130 degree processing temperature, and the green is a 150 degree processing temperature plus a vacuum. So in this last treatment, the idea was, let's make sure that the aggregate is dry. You know, back where I come from, they use the expression bone dry. I don't know what it really means, but I don't think bones are necessarily dry, but that's the expression. So it's very dry. Now, so what you see here is you see scatter, and you see different reactions between the asphalts and the aggregates. But the one thing that you can take from this is that with certain combinations, getting the asphalt or the aggregate real dry, getting rid of that little interlayer of moisture, really changes the adhesive bond that occurs. In others, it doesn't make a lot of difference. And you can also say that, you know, between 90 degrees and 130, there's not a big difference either. But when you go through this process of a high heat and a high vacuum, really drying the surface, it makes a big difference. What do you glean from that? Well, I'm not real sure exactly, other than the fact that there are certain combinations of aggregate and bitumen with which we want to be careful in terms of our processing. And it may mean that certain combinations may not perform as well as others in a warm mix environment, because that little inner layer of water really compromises the bond strength. Okay, so I've given you two examples of some fundamental knowledge, surface-free energy and enthalpy, the heat of interaction between an asphalt and an aggregate. Both of them are related to the bond strengths that develop between the asphalt and the aggregate. We want that high level of adhesive bond strength so that we can resist moisture damage. Well, how do you use something like that? Well, the way you use it is to evaluate the constituents so that when we select the constituents, if we have that opportunity, we can select the ones that have the greatest potential to resist moisture damage in the mix. And then we have to make sure we have good mix design, obviously. So we've made a good selection choice. And that's really what we say when, that's really the point of this. Okay. Now the next thing I want to discuss is a model that we are developing at Texas A&M with some of our colleagues. University of Illinois, we're working with University of Illinois using their expertise in pavement tire interactions. And this constitutive model is called PANDA. PANDA is an acronym that stands for Pavement Analysis Using Nonlinear Damage Approach. And of course, we needed to have an acronym that people could recognize. So PANDA is, there's a panda bear. You could put a picture of a panda bear on the top of a CD and people would sort of recognize it. And so we didn't want to call it pavement analysis using nonlinear damage approach. We started out with words and tried to fit the title to it, but that's another story. So this particular model characterizes the asphalt mixture based upon a nonlinear viscoelastic and viscoplastic approach in which temperature, of course, is a huge player. So we call it thermo-viscoelastic, thermo-viscoplastic. So when the asphalt mixture is characterized in this way, we then evaluate the stress tensor under a certain load to evaluate mechanical damage. If the stress tensor exceeds this yield surface based upon the level of how much it exceeds the yield surface, damage is calculated within the asphalt mixture. And the yield surface is allowed to grow as damage occurs. So it's a pretty sophisticated model of damage. But what I really wanted to emphasize to you, that with that model, we've coupled a number of other processes. I mean coupled, so they don't have to be done separately. They can be done individually. The mechanical damage can be done individually, but we could also integrate with it or couple with it the moisture damage process that we've just sort of introduced. We can also integrate or couple with it healing. During rest periods, we know that micro cracks in areas of very small amount of damage can actually recover during these rest periods. And there are certain chemical components, compositional nature of the asphalt that can promote healing. So healing is something else that we have integrated or we have coupled with this analysis system. And then finally, we have coupled with it the process of oxidation. Now, oxidation and moisture are integrated into this model in a similar way. In oxidation, oxygen is diffused or diffuses into the asphalt. As it diffuses into the asphalt, it changes the chemistry of certain functional components of the asphalt, and that changes the characteristics of the asphalt mixture. So this is our system. So what I want to do in the next few minutes is to just give you an idea of how we have approached the process of moisture damage within the PANDA system. All right, so as a review, in an asphalt pavement, moisture will move into the pavement. How does it move into the pavement? Well, we have capillary rise, we have moisture gradients, relative humidity gradients, we have temperature gradients, we have infiltration from the surface. It moves through the voids, it moves through the cracks, and then it diffuses into the mastic, perhaps softening the mastic, compromising the cohesive bond strength. When it gets to the interface of the mastic and the aggregate, it compromises the adhesive bond strength. So there are two processes that we want to be cognizant of: the decay in the cohesive strength, the decay in the adhesive strength. And we talked a little bit previously about how the thermodynamic, the chemical, and the other effects impact this. So within this constitutive model, we have an evolution function that models rather phenomenologically, I hate to say. We can't get quite too mechanistic on it, the moisture damage process. So here what we're saying is that the rate of moisture damage, which is this little Greek symbol here with a dot on top, the rate of moisture damage is a function of the moisture content theta at a specific time. That makes sense. And the model also says that with time, even if we keep it at that moisture content, with time it will continue to degrade. And that's defined by these terms right here. And it also says that there's a history effect. And that's defined by this term right here. And that exponent Q. And that history effect says that as the moisture damage continues, that the rate will change. So it's a rate of moisture damage that's going to be a function of the moisture content at that time. And if it maintains at that moisture content, it's going to degrade with time. And the rate at which it degrades and the impact of the previous damage history are integrated into this evolution function. Well, you don't have to understand it. It took me a while to get used to it. But all I want you to know is that the evolution function accounts for those things. And we have validated it against laboratory test data. Okay, so how does moisture get into it? Well, most models like Abacus and others have built in a fixed second law diffusion type process. So we're pretty lucky there, and that's the way we think that's a good representation of the way moisture moves and the way that oxygen moves within an asphalt material. In this little movie, we look at fixed second law, which just says that the rate of moisture change is the diffusivity coefficient times the gradient of concentration gradient times the moisture content. And so if we look at a microstructure, which would be a microstructural element of aggregate within a mastic, and we say we're saturated up here at the surface, and that we have we're half that level of saturation along the sides, and we use fixed law, we can see how the moisture progresses through the system. And then over here, we have a pavement structure where we're saturated at the surface, and we're watching moisture permeate down through the pavement. Okay, no big deal there. It just gives you an idea of the diffusion rate using fixed second law. Remember, we're saturated at the surface, and we have half that level of saturation along the sides. So it shows you that the contact with higher levels of moisture are going to begin to develop a high level of moisture first, and then it will trickle on down to the other areas. Now let's look at another microstructural schematic in which we're modeling the aggregate as elastic entities, and we're modeling the mastic as a material through which moisture can diffuse. And let's look at this schematic approach and the decay of the adhesive and the cohesive bond strength as moisture moves through the system. So we start out with a little element up here, and we magnify it. We can provide some interstitial elements along the boundary of our elastic aggregates, and we can give those elements a different evolution relationship that will affect the adhesive bond, and then we can characterize the purple area, or the darker blue, which is the mastic, with the cohesive rate of moisture damage, using the particular evolution function for it. And then as the process occurs, if we allow diffusion to occur according to fixed second law, it will continue to progress through that element, and we can chart the decrease in bond strength in our micromechanical model as a function of time. Since we can have the ability to evaluate cohesive damage separately from adhesive damage. As the moisture permeates through the system in this micromechanical model, we can continue to evaluate both processes. Now, how would something like this be functional? How would it be used? Well, if you're trying to determine, if you have a specific aggregate, if you have a specific binder, using some of the tools that we previously discussed, you can get an idea of how well they might fit together to resist moisture damage, and you can actually evaluate their potential for adhesive or cohesive damage. You can do it through computational, computing the actual adhesive and cohesive bond strengths using surface energy, or you can measure it directly using something like a pull-off test. Now, with the time limitations that we have, I don't have the time to go into all the details of this, but I just wanted to show you that it's something that can be used on a micromechanics level, so you could use it, for example, in mixed design. You could try different aggregates, try different binders, and look at the progress of moisture damage both at the adhesive and cohesive level before you get to the actual pavement analysis. Okay, if you continue on in your micromechanical analysis, that was moisture damage that we just looked at. That was how the cohesive bond and the adhesive bond is compromised as moisture diffuses into the system. Now, if you add on top of that, if you couple with that the mechanical damage under repeated loading, or static loading for that matter, you can see how the average compressive strength versus stress-strain curve diminishes from a dry state to a aged material. So this is, the dry state. This is the mechanical damage, and showing it in red here. This is the after 3 days of moisture diffusion, and you can see the more red area, more damage kind of concentrating at the surface and along the edges where the moisture contacts the micromechanical element. And then this, after 10 days, you see more damage, and 30 days, you see more damage. And not only can you see where the damage occurs, where it's localized, but you can also quantify the amount of damage, as you can see through the stress-strain curve here. So that is a tool that can help with virtual experiments where you select different components. You have a mixed design. You have an idea of your distribution of aggregates, perhaps through tomography, and you can run some simulations before you make actual selections. Well, let me close by talking about the pore water pressure effect. We've got this model, the PANDA model, that we've talked about and running in pretty good fashion. Remember, it uses a viscoelastic, viscoplastic characterization of the mixture. We couple with that the impact of moisture intrusion, oxidation diffusion, and healing to evaluate the total damage process. One of the things that we sort of left out along the way was pore pressure. And we have to account for the pore water pressure in our model. We've now integrated pore pressure, the effect of pore pressure, but not the effect of the moving water through the voids, scouring effect. That's going to take a little bit of time. So as we move into these voids, we've got a pretty good handle now on pore pressure and how it aggravates the damage within the cohesive mastic, the cohesive damage within the mastic, and the adhesive damage along the interface between the mastic and the stone. But what we haven't been able to get to is the dynamic effects of the moving water, and that's what we're working on right now. So let's take a look at the pore water effects. If we just look at the pore pressure alone and its impact, we find that if we calculate damage density using our previous model, which characterizes the asphalt viscoelastic, viscoplastic, and couples with that the effect of moisture intrusion, if we look at that, we get this damage density as a function of load cycles in red. But if we add the effect of pore water pressure to it, if we couple that in there, then you can see a significant shift where we have a higher level of damage. So it's something that's real important and certainly something that deserves more work. Let's look at another micromechanical model. And here we have an aggregate. We've got a mastic, and we've got the cohesive or adhesive zone that where the coupling of the mastic and the aggregate is modeled. And this time we have an air void in here. So we're going to look at a finite element mesh, and we're going to include the effect of pore water pressure and see what that does. Let's look at a little movie here that shows the deviatoric stress distribution. This is going to be where we have the micromechanical element with no air void, the micromechanical element with an air void and no pore pressure, and the air void here plus pore pressure. And what you're seeing in these particular micromechanical models is going to be, let's see, excuse me. Oh, got the wrong one. Is the deviatoric stress. If I can find my cursor. Okay, so this is the air void, no air void, the representative volume element with no air void. We're looking at the application of load, and we're looking at the deviatoric stress distribution. And where you go from the blue to the lighter and hotter colors, you have a higher concentration of deviatoric stress, or a higher level of deviatoric stress. So with the air void itself, you see a little bit of concentration of deviatoric stress. And when you add the pore pressure, of course, you see a great amplification of the level of the deviatoric stress. Well, higher deviatoric stress is going to cause a higher level of damage. So here we look at the two representative elements. Come here, cursor. Two representative elements. In this case, there's no pore pressure in the void, and in this case, there is high pore water pressure in the void. And of course, you see a much higher concentration of damage, and it occurs more quickly. The time lengths are synced, so the rate of damage is illustrated there as well. If you were to graph that, or if you were to plot it, you would see the stress-strain relationship. The blue represents no pore pressure. The red represents the rapid mobilization of stress, and you can see that it is a weaker material as well. So all of that is helpful in allowing us to look at micromechanical simulations of the effect of pore water pressure coupled with the effect of the softening and weakening effect of moisture intrusion. So finally, I want to show you just a set of data for a pavement. And I want to just remind you in terms of the pavement, the continuum damage analysis. What we do is we evaluate the damage over an element, and then we sum the damage over the different elements, and we compare the damaged system versus the undamaged system to get an idea of the percent of damage. And if we want to calculate rutting, the magnitude of rutting within a pavement layer, we use the viscoelastic, viscoplastic characterization, and we calculate the viscoplastic strain, multiply it by the thickness of that element, and then we sum up all the elements to quantify the magnitude of rutting. And so this is a final representation of what happens with a full-scale pavement analysis with the wheel tracking back and forth. And in this particular example, we have used Fick's law to allow diffusion of moisture. And then we have applied the evolution function of moisture damage, and on top of that, we have coupled mechanical damage. So using that integration technique that we talked about, we're able to get the contours of high level of damage, where it occurs and the magnitude of that. From the result of this analysis, you can see that if we calculate rutting, this is rutting in millimeters, and this is time, that as we have higher moisture contents, we get a higher level of rutting and a quantification of that level of rutting. So the red dot represents dry, and then we go to the green. That's a 0.2 theta value, meaning a higher moisture content, and then a 0.6 and a 1. So you can see as the moisture content increases through diffusion, we get a higher level of damage, and that's defined by this evolution function. Well, I'm sure I'm getting close on my time. So what I wanted to show you in this brief treatment here today was that we can use fundamental concepts such as surface free energy and enthalpy measurements to assess the potential for moisture damage, to help us select an aggregate and a bitumen that would be resistant to moisture damage. And then we have developed a rather sophisticated continuum damage and micromechanical model of the pavement system that we can also use to evaluate aging effects and moisture effects. And in terms of moisture, we have coupled the effects of diffusion, moisture damage, and mechanical damage. It considers damage within the entire system or at an interface or within the mastic itself. It considers pore water effects, and then other water movement effects are now being considered and included in the model. It can evaluate pavements at the different length scales. You can do virtual experiments on mixtures and evaluate a pavement, a full-scale pavement as well. So thank you very much for your attention after lunch, and I'm open for questions.